Now in 10.1, we have seen that the parametric equation that we have will be x and y, where x is a function of time t and y also a function of time t. Now in the past, we have that x is our independent variable and y our dependent variable. So basically y as a function of x, we can therefore write the y equals to a function of x like this. Now sometimes we write y equals to fx, right? But we can actually write y as a function of x using this notation also. Okay, you can stick with this, but basically y as a function of x can be written either way. Now, in parametric equation, however, in parametric equation, the independent variable is t, and our x and y's depends on that t. Therefore, the notation we use is basically this notation here. X as a function of t and y also as a function of t. Okay. Now, furthermore, the reason I want to go back to this notation here because of the following. Now, because y was a function of x, then if I go a bit to the right, because y is a function of x, then when we write y prime, it is understood as the derivative of y respect to its independent variable. Okay, you usually write it more complete notation, y prime of x equals to dy dx. Right? That's what we did in the past. Now, right now, because x is a function of time t, then when we write y prime later on, this has, x prime, then this will be understood as dx dt. Likewise, because y is a function of time t, then y prime will be understood as dy dt. Okay, so what I want to say is like this prime notation that I use here is consistent to the way we define the prime in calculus 1. Okay, so y prime is now not equals to dy dx. Okay, that was correct in calculus 1 or prior to this lesson because y is a function of x. Right now, y is not function of x. Y is a function of time t. So y prime should be understood as dy dt, not dy dx. You see what I mean? Now, then we will go back. So how do we define dy dx then? So dy dx, that's the derivative of y respect to x, therefore will be done in the following way. This is dy dt. We do the derivative respect to t multiplied by the chain rule dt dx. Okay, that's basically chain rule. Which we can write in the nicer way. This is dy dt on the numerator divided by dx dt on the denominator. So basically, the derivative of y respect to x, the derivative of y respect to x is equal to y prime over x prime. To be more precise, y prime p over x prime p. Okay. Now, how about the second derivative? The second derivative of y respect to x, this should be seen as the derivative of dy dx respect to x. But again, we have issue with doing the derivative respect to x. We have issue with that because our y is not a function of x. Our y is a function of t. So if I need to take the derivative respect to x, I need to do chain rule. Okay, I need to do chain rule, and that will be the derivative of dy dx respect to t times the derivative of t respect to x. Okay, I hope you can see the chain again there, which is basically equal to the derivative respect to t of dy dx divided by the derivative of x respect to t. Okay, now that's for the second derivative. Now, of course, those are the theory, but with this theory, we have enough to do some questions. Of course, I will put more details later on. Now, let's see. For example, if I do problem from our textbook, let's do, for example, question number 4. Question number 4. We have our x equals to 1 minus, I'm sorry, that's t minus t to the negative 1, and y be 1 plus t squared. Now we want to find the equation, of the line tangent to the curve. We usually say this is curve C here. Okay, curve C, this curve C at t equals to 1. Now, to find the equation of a line, we need two things. First, we need a coordinate, the coordinate that the line passes by. And then second, we need the slope of the line. Okay, so let's find the coordinate first. What is the coordinate that this tangent L actually pass by? If we try to imagine that, let's say this is the curve. Okay, let's say this is the curve. And at time t equals to 1, we try to find the tangent line. Let's say this is our line L here, and this is our curve C here. Okay, I need to find the coordinate of that t1, t equals to 1. Now, how to find the coordinate? First, to find the coordinate, we find what is x when t equals to 1, what's the y when t equals to 1. Correct? When t equals to 1, x will be 1 minus 1 to the negative 1. That's 1 minus 1 equals 0. And as for the y, when t equals to 1, I get 1 plus 1 squared. That's 1 plus 1, that's 2. So the coordinate will be 0, 2. Okay, the coordinate that the line will intersect, the coordinate where we observe the tangent line later on will be coordinate 0, 2. Okay, now second, we need the slope. We need the slope m. But to find the slope, we need to find the derivative of y respect to x when t equals to 1. Now let's find what will x prime be and y prime be. X prime t will be 1 plus t to the negative 2, and y prime t will be 2t. So x prime 1 will be 1 plus 1, that's 2. Y prime 1 equals to 2. Therefore, dy dx at 1, at t equals to 1, notice that this guy is actually y prime 1 over x prime 1, right? That's what we have up here. That's what we have up here. You see what I mean? Okay, now then that's equals to 2 over 2, which is 1. So now we have the slope is equal to 1, and it passes the coordinates 0, 2. Now you can do it yourself. I mean, at this point you have to know this. Okay, then the equation of the line tangent to the curve at t equals to 1 will be y equals to x plus 2. Okay, that's the equation of the line tangent to the curve at t equals to 1. Let's see another question, number 8. It's actually quite similar, but they worded differently. Number 8, we have a parametric equation. Curve C is given by x equals to 1 plus square root of t, and then y equals to e to the t squared. And we want to find the equation of the tangent line to the curve by A, without eliminating parameter, and then second by first eliminating parameter. I will just do part A. Okay, I want to find the equation of tangent line to curve C at 2, e. Notice this time they don't give us the time t, but they give us the coordinate. Well, then we need to find the time first. We have the coordinate already, right? But I need to find the time. I need the slope, right? I need the slope. But for me to find the slope, I need dy dx and the time. Is it right? So I will need to find the time. I will need to find y prime t and x prime t. That's the idea. Okay, so what I will do first, let me find the time first. How to find the time. Then we set it equal to x equals to 1 plus radical t. That should be equals to 2. So what will t be? Square root of t equals to 1, then t must be 1. Right? And you can confirm using the second equation. Y equals to e to the t squared. We need to set this equals to e. Therefore, t squared must be 1. Right? T equals to plus minus 1. But the common t that we can have here is t equals to 1. So we know the time now. We know the time now. Let's find the derivative. Then x prime t will be 1 over 2 square root of t. And y prime t will be e to the t squared times the derivative of t squared is 2t. Then I plug in t equals to 1. I will get 1/2 for this one. When t equals to 1 here, I will get 2e. Therefore, y prime 1 over x prime 1, that's equals to dy dx at time t equals to 1. That's 2e over 1/2. What will that be? That'll be 4e. Okay. So right now we have the coordinate is 2e and the slope is 4e. Okay, so the equation of the tangent line will be y equals to 4ex plus some number. 4ex equal plus some number. I think let me see, when I plug in the coordinates, e equals to 4e times 2 plus d, that's 8, so the d will be negative 7e. Okay, so the equation of the line is given by y equals to 4ex minus 7e. Okay, now let's go a bit further. I would like to use the, let me do one more question. The following question is actually quite similar, but it goes a bit further than just finding the equation of the tangent line. Let's say I pick the easy one first, number 12. Let's see the given by this parametric equation. X cubed plus 1x equals to t cubed plus 1, I'm sorry. And then the y will be t squared minus t. And the question is part A, find dy dx. So find the derivative of the curve as a function of t, of course. And then second, we need to find dy d squared. D squared y, I'm sorry, it's too small. D squared y dx squared. Basically, the second derivative of y with respect to x. Okay, so for part A, x prime t will be 3t squared. Y prime t will be 2t minus 1. Okay, therefore, dy dx, of course, as a function of t, will be y prime t over x prime t. Is it okay? Now, so far we use this first derivative to find the equation of the tangent line at certain t or certain coordinate. But I want to go a bit further. One very common question, so I already answered part A, but I want to use that part A to answer some follow-up question. For example, at what t will the tangent line be horizontal? And the second one, how about at what t will the tangent line be vertical? Okay, now as you can see, horizontal tangent line is when the slope is equal to 0, right? Basically, when, in other words, that's when the dy dx equals to 0. Okay. Now, dy dx equals to 0. By the way, dy dx we know is y prime over x prime, right? Now, that implies the slope is equal to 0. The slope is equal to 0 when y prime t equals to 0, but the denominator x prime t cannot be 0. Okay. Otherwise, if you have 0 over 0, then it's undetermined. Okay. So we need the numerator be 0. The denominator cannot be 0. How about vertical tangent line? That's when the slope is undefined. Now we can say that when dy dx is undefined, but actually I prefer to say that the dx dy equals to 0. Before we go on, let's do a little analysis on the following figure. Now, dy...
Professor, can I ask a quick question?
Yes.
For the undefined, why is it dx dy equals 0 and not dx dt equals 0?
Not yet, later on.
Okay.
Later on.
Okay.
Mm-hmm. I tried to explain first the idea of horizontal tangent line and then how to relate it to vertical tangent line. Okay, now, so what happened is this. For horizontal tangent line, see, this is the point here, okay, the tangent point. Notice that the tangent line is horizontal if the slope is equal to 0. I mean, that's something we know already, okay? But the slope equals 0 is when y does not change when x changes. When x change, the y doesn't change. That's why it forms a horizontal tangent line. Is it okay? Now, using the same similar idea, I go for the vertical tangent line. This vertical tangent line here. This, we know that the slope is undefined. But to be more precise, you see that the x does not change along that line. Along that line, you will see the x does not change when x changes, when y changes. Okay, so you have the situation where dy dt is not equals to 0, but the dx dt is 0 at that point. Okay, now that's the explanation how I actually move from, if the slope is undefined, basically it means dx dy equals to 0. Okay, if the slope of the tangent line is undefined to give us a vertical tangent line, then the dx dt is equal to 0, but dy dt is not equal to 0. Now, which, if you think about this further, I use a green color right now. This is basically x prime t. That's basically x prime t over y prime t equals to 0. Therefore, we can say we have a vertical tangent line when the slope is undefined, and that is when x prime t equals to 0, but the y prime t is not 0. A very similar logic to what we have up here. Okay, so if this quotient equals to 0, then the numerator is 0, but denominator is not. Now, we apply the same idea. This expression equals to 0 is when the numerator is 0, but the denominator is not. Okay, now, so let's look back to our question. We have this right now. We have this derivative of the parametric function. let's find the coordinate where the curve has a vertical and horizontal tangent line. Oops, what happened? Why it looks like this? Oh, that's not what well, anyway, I write it here. So if I look back, so my C is given by what again? T cubed plus 1, x equals to t cubed plus 1, and y equals to t squared minus t. And from there, we get that x prime is 3t squared, y prime is 2t minus 1. So where do we get the horizontal tangent line? Horizontal tangent line when y prime is equal to 0, but x prime is not. Okay, basically I will use that y prime, the 2t minus 1, set it is equal to 0. That's how I get t equal to 1/2. And you check, you need to make sure that when you plug this t in, it's not 0 into the x prime. Basically, you will see that's not equal to 0. Okay, so the coordinate when C reach slope equals to 0, the slope of the tangent line equals to 0, it may be the local maximum, maybe the local minimum, maybe just an inflection point. Okay, is when t equals to 1/2, which implies the coordinate is 1 and 1/8 for the x, negative 1/4 for the y. That's basically x 1/2 and y 1/2. Okay. Now, how about the vertical tangent line? Vertical tangent line. That's when x prime equals to 0, but y prime is not equal to 0. The question that you need to answer later on, what happens if both of them 0? Then we need to apply limits. Okay. I hope later on we can find that kind of question, but for now we just apply the idea. Okay. X prime equals to 0 means 3t squared equals to 0, blah, 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 t equals to 0. Now I need to make sure that the y prime is not 0. Y prime 0 is 2 times 0 minus 1. That's not equals to 0, so we are fine. Okay, now then coordinate when C has vertical tangent line. Let me call this vertical tangent line. Is when t equals to 0. That is when the coordinate is 1, 0. Okay, now that's the follow-up question for part A. what is the reason we want to find the first derivative? Well, because the first derivative helps us to see the shape of the graph, actually the tangent line, the slope of the line tangent to the curve. Okay, now part B, how about the second derivative? How about the second derivative? Now the purpose of the second derivative is to look at the concavity. Is it concave upward or concave downward? Okay, now as we have seen that the second derivative of y respect to x is the chain rule of the derivative of dy dx respect to x, respect to t, divided by dx dt. Okay, so let's get that dy dx first. Something we get from part A. I think, what's that? Dy dx 2t minus 1 2t minus 1 over 3t squared. And that's 2t minus 1 over 3t squared. Now then, what is the derivative of dy dx respect to t? When we do quotient rule, right? Quotient rule will be the denominator will be squared. The numerator, we have the derivative of the top times the denominator minus the top times the derivative of the denominator. Simplify. Combining like terms, negative 6t squared plus t over 9t to the 4th. I'm sorry, it should be 6t. Let me simplify it a bit. I will factor the 6t on the top. So I will get 1 minus t over 9t to the 4th reduced by t and 3. 2 times 1 minus t over 3t cubed. We are not done yet. This is just the derivative of dy dx respect to t. Now, then, the second derivative of y respect to x will be on the numerator. On the numerator, we have this guy. Okay, that's equals to, on the numerator, we have 2 times 1 minus t over 3t cubed. The denominator, we have dx dt. What is dx dt again?
Is it 3t squared?
That's right, that's 3t squared. Okay. I use this color here to help you see how I actually just doing a Lego here. Okay, plug and play substitution thingy. Okay, so I have 2 times 1 minus t over 9t to the 5th. Now, then the follow-up question here, which actually in our book, okay, for which values of t is the curve concave up? For which t is c concave up? Well, concave up is when the second derivative be positive. Right? That's something we know from calculus 1, by the way. We just apply that idea now into this parametric. Okay? So I need to solve this 2 times 1 minus t over 9t to the 5th. This guy has to be positive. Now, how do we solve that inequality? Then first, something we're supposed to learn in intermediate algebra, and we see again in pre-calculus, and we see again in calculus 1, and we now see again in calculus 2. To solve nonlinear inequality, you need to do first the critical numbers. The t in this case, where the sign may change from positive becomes negative or negative becomes positive. T equals to 1 for the numerator, and t equals 0 for the denominator. Okay. Now then step 2, we do the sine graph. Then t equals to 0 and t equals to 1. When t equals to 1, the value is 0. When t equals to 0, the value of this expression is undefined. Let me slow down a little bit here. I hope you know what I'm doing. Now then, from there, I do the sine graph. Let's say I pick t equals to 2. When t equals to 2 and I plug it in there, 2 times 1 minus 2 over 9 times 2 to the 5th. Is it positive or negative?
Negative.
That's negative. Okay. And you do likewise, or if you are pretty good with your pre-calculus, you notice that t is 0 with multiplicity of 1, which means when you jump across that 0 with multiplicity of 1, critical number with multiplicity of 1, you change the sign. Basically, if the multiplicity is odd, you change the sign. If the multiplicity is even, you don't change the sign. Okay, now then from there we can answer the question. Basically, to answer the question, for which t is the curve concave up? Then when the t gives the second derivative to be positive, right? Greater than 0. Okay, so C is concave up on the interval from 0 to 1. Okay, now we can actually use these informations here to actually help us graphing. Hopefully it works. Okay, let me try. I don't promise you. So let's say we have a coordinate system here. Okay, and then what coordinates we have? Well, I happen to see on my screen here, I have 0, 1. Let me use that one. So I have 0, 1. That's 0, 1. What other coordinates do we have? 1, 0. That's the vertical tangent line. That's 1, 0.
9/8 over 9/8 negative 1/4.
9/8 negative 1/4. So a bit more than 1, negative 1/4, approximately here. 1.125, negative 0.25. I think we only have those, huh? When t equals to 0, and then when t equals to 1/2, what else? And when t equals to I'm sorry. I'm totally wrong. This 0, 1 here is not the coordinate. Duh. It's not a coordinate. That's an interval. I kind of misinterpreted as a coordinate. No, it's not a coordinate. Oh man, that's a very bad mistake. Well, at least I have these two coordinates. Nothing you can draw with this, right? Let's plot some coordinate. So when we do the table, let's say we do the table when t equals to what, y equals to what, x equals to what, y equals to what. So when t equals to 0, we know the x is equals to where's the equation again? Let me pull it down. Where's my equation? Here. Hopefully it helps us to see how they behave. When t equals to 0, the x is equals to 1, and the y is 0. When t equals to 1, the x is 2, the y is still 0. Oh, 2, 0. I think this is when t equals to 1/2. So this is when t equals to 0, t equals to 1/2. This is t equals to 1. When t equals to 2, I get x equals to 9, the y equals to 2. So it goes very far there. How about when t equals to negative 1? The x is 0, the y is 2. Okay. Now we know that between t equals to 0 to t equals to 1, it will be concave up. And then from there, it will be concave down. To be honest with you, I don't know what it will look like. Oh, hold on. It has a vertical line. Where's the vertical line? It has a vertical tangent line at 1, 0. Oh, line should be vertical here. Kind of vertical before it kind of change direction. Okay, let me depict that. The horizontal tangent line is for this part. That's the horizontal tangent line. Okay, and then the vertical tangent line is for this. It has vertical tangent line tangent at this point. Okay, honestly, I don't know what it looks like if I go increase the t later on. You can plot more coordinates, and when I decrease the t later on, I know it will be concave down. I know it will be concave down when I go to the left, and I know it will concave down also when I go to the right. It will be concave up only here. Okay, yeah. At least I get important coordinates. What are the important coordinates I need? I need this guy, this guy, this guy, and actually I get the x-intercepts and the y-intercepts, right? Actually, it has two x-intercepts, that's right, and one y-intercept, that's right. Okay. Let me put a note here that this part here is unknown. This part here, I don't know what the graph. What we know is concave down. Concave down. Okay. Concave down. Okay. Now let's try to graph these functions. Okay. Let's try to graph this function. I have the software, which at which we are actually able to graph that. Now, somebody help me finding what's the x again?
For the original?
Yeah.
Looking for the equation?
Yeah, t
Two
cubed
plus 1.
plus 1. T cubed.
T squared minus t.
Plus 1, and then the one for the y, that would be t squared minus t. We only see that little portion there. Do you know why we only see this little portion? Because of this. Do you see the parameter? Do you see this in your screen? That the parameter t only moved from 0 to 1. Right? And according to our picture, from 0 to 1 is where the graph actually concave up. Now, if I want to see better picture, I will change the lower bound. Let me make it -5 for the, maybe -3 for the t, and then the upper bound, let me make it 2. As I remember, that's quite big already. That's what it looks like. If I zoom it out further, that's what it looks like. Oh, wow, that's quite far for that -3. Wow, that's really far. Yeah, for that -3 is stuck there. So when t is equals to 2, it's here. When t equals to 2. Okay, when t equals to 2, it's here. Remember we did that when t equals to 2. Let's look back here. When t equals to 2, we get this coordinate here, 9, 2. right? This coordinate here is 9,2. Do you see that? Okay. And then when t equals to -3, the coordinate is here. Okay. And from this graph, you can see that it is concave up only when t is equals to 0 to t equals to 1. Let me enlarge that. Move it to the middle and enlarge that so that we can see a better picture. Okay, that's what it looks like. If I want to put details, let me put the details here. This is the point where we reach the horizontal tangent line. Right? You remember that? Okay, and this is the point where we reach the vertical tangent line. You see? Okay, and this is when t equals to 0. This is when t equals to 1. Okay, so between t equals to 0 to t equals to 1 is concave up. From t equals to 1 and on, even though it looks like a straight line, it's actually concave down. It's slightly lower than a line there. Okay, and when t is negative, you see it's still concave down, right? Now compare this graph, the actual graph here, with the sketch I have. You see? Okay, now the sketch I have is not nice, I know, but I get all the important features of that graph, especially the vertical tangent line, horizontal tangent line, concave up and concave down. Okay,
I have a question. What if we wanted to show the direction for this one?
The direction is actually there. Happens to be easy because this is t equals to 0, this is t equals to 1.
Yeah.
So it must be going this way.
Going to the right?
Yeah.
Okay.
Yeah, happen to be though. It's not always.
Okay.
Yeah. But we just plot that when t equals 0, where, t equals 1, where, and then from there you can see the direction.
Okay. I think we still see the graph that you did on the program.
Oh, I'm sorry. This is what it looks like. My bad. So this is the sketch. Okay, and this is the, oh, thank you. Let me know right away. Yeah, and this is what the graph look like. Okay, the actual graph and with the important features from that. Now, in pre-calculus, the main question you had at that time was finding the x-intercept and the y-intercept. Right now, in calculus 1 and spill over to calculus 2, is to find the coordinates where we have horizontal and vertical tangent line. And of course, in calculus 1, we already learned concavity. We can apply that also here. Okay, now that's for this one graph. Let's go on one more question before I give you a break. I hope this is the question that I would like to have. Number 18. The curve is given by x equals to t cubed minus 3t. And oops, what happened? And then what did I do? And then the y is equal to, you know what? I think it's possible. Okay. Y equals to t cubed minus 3t squared. And the question is, find the points on the curve where the tangent is horizontal or vertical. It seems to be a question we already did. Okay, but let's try to work it out. Let's try to work it out and see. I expect to have some issue when we try to work it out. X prime will be 3t squared. Huh? I didn't move though. 3t squared minus 3, and then y prime equals to 3t squared minus 6t. Okay, so let's break it up. The horizontal tangent line means, oh, what happened? I'm sorry, something wrong with my pen. The horizontal tangent line is when y prime equals to 0, but x prime is not equal to 0. Right? When y prime equals to 0, so we get 3t squared minus 6t equals to 0. Let me factor the 3t out. So we get t equals to 0 and t equals to 2. I'll check. X prime 0 will be negative 3, which is not 0. And x prime 2 will be, what happened? Give me a second. Anybody do Zoom bombing me?
Do what?
Zoom bombing. Like somebody try to interrupt with my lecture.
Is your stylus maybe low on battery or something? Because I noticed that happens with mine.
Mine is not with battery.
Oh, okay.
Yeah, my stylus without battery. Let's see. Okay, so when t equals to 2, x prime 2 will be 2, that will be 9. I think so. 12 minus 3 is 9, which is not equal to 0. Okay, so horizontal tangent line will be when t equals to 0, which means the coordinate is 0, 0. When t equals to 2, the coordinate will be 2, 8 minus 12, that's negative 4. Now for the vertical tangent line, we have x prime is equal to 0, but y prime is not equal to 0. Let's see. When x equals to 0 means x prime equals to 0 means 3t squared minus 3 equals to 0. T squared equals to 1, so t equals to plus minus 1. We check that on the y prime. So So y prime 1 will be -3. That's not equals to 0. Oh, so we are fine. Y prime -1. That will be 3 plus 6. That's 9. That's also not equal to 0. Oh, then we are fine. Then when t equals to 1, we get -2 comma -2. When t equals to -1, that's 2 comma -4. Ah, do I compute it correctly? When t equals to -1. Yeah, okay. See, the reason I stopped a little bit because I noticed that we have the same coordinate, right? But different time reaching that coordinate, right? So we have some kind of loop here. We'll have some kind of loop. Okay, we'll have some kind of loop. Well, anyway, we get what they want us to do. I need to look for the type of question that is quite strange later on. But let's take a look what the actual graph look like. Yeah, having this software enable us to confirm what we have. So number 18, that's t squared minus 3t. I'm sorry, t cubed minus 3t, and then t cubed minus 3t squared. Oh, what does it look? Ah, that's what it looks like. Should I extend this a bit? Yeah, that's what it looks like. So you see, as we expect earlier, let me copy this. As we expect earlier, that we have horizontal tangent line at 0, 0, right? And another horizontal tangent line at t equals to what?
Two.
T equals to 2. Okay, so when t equals to 0, we have a horizontal tangent line. When t equals to 2, we also have horizontal tangent line. Now, the vertical tangent line happens when t equals to when t equals to 1, that is -2 comma -2, right? This is when t equals to 1, and then when t equals to -1. Happens to be the same coordinate, okay, but different time. Okay, this is t equals to -1. Okay, and what is the direction of the graph, by the way? Well, we start from t equals to -1, going to t equals to 0, and then t equals to 1. So it goes in this direction. Okay. Now that's for this derivative, the first derivative, and then tangent line, horizontal tangent line, vertical tangent line, and the second derivative, and the concavity. Now, after the break, we will learn how to apply this to find, for example, the area, the arc length, and the surface area of revolutions, which you will see only substitution coming into play. But let's take a break first. Right now it's 5:42. We come back at 5:55 then. We will continue now to finding the area under the curve. So we have the following topic, but we already have all the foundations we need. For the area, we need the area, and then we need arc length, and we need to have surface area of revolution. I really think, I don't see that in our book, but we actually can also find the volume of revolutions. But let's see later if we have time, okay? Now, how about the area? Now, the area under the curve, so let's say we have a curve. Let's say this is A, this is B, and at time t, at time, let's say t1, that's the location, and this is the time t2. Okay, and we are interested in finding the area under the curve here. Now, the formula that we have before from calculus 1 is that the area equals to integral from A to B of fx dx, is it right? Where our fx is actually just a y, agree? Now, notice that our x is a function of t, and our y is also a function of t. So what is the dx? Dx dt is equals to x prime, right? Now then we can substitute our dx later on as x prime dt. Okay, so here's the thing. Our formula here gets substitution becomes A equals to integral of the y now as a function of t instead of function of x. Right? This guy now becomes this. The dx becomes x prime t dt. Do you see that? Right? And then the limit of integration, instead of from x equals a to x equals to b, now it becomes t1, t2. Is it okay? Now, by the way, it actually depends on the direction of the movement. In this case, we assume that the curve actually moves in this direction. Okay, but suppose if the curve is actually moved backward, then you need to reverse the order of T1, T2. You see what I mean?
Can you repeat that, please?
Yeah. In this case, the T1 is on the left-hand side, the T2 is on the right-hand side. And we move from left to right. So the ordering for the T's is from left to right. Okay. Now, suppose the curve actually going backward. Suppose the curve is actually going this way. Let's say this is the T1 and this is the T2. Okay. Then the area for this case, that will be integral from T2 to T1 because T2 is on the left-hand side. Okay, and the one inside stays the same. That's basically YT x prime T dt, like that. Okay.
Will that be made known, or will we have to determine which way the graph is increasing or decreasing?
You actually need to determine that, but you will see that that will only reverse the positive becomes negative, negative becomes positive. So to be honest with you, I don't really like this approach, but somebody actually used this formula and said the area equals to the absolute of integral T1, T2, just to make sure that it will always be positive. Like that. Yeah, because imagine if it's supposed to be T2 to T1, but what you did is actually T1 to T2. Because of that reverse order of integration, right? The limits of integration being reversed, you should get the opposite. Let's say the area is supposed to be 5, you end up getting -5. You see what I mean?
Yes.
Okay, so if you see the situation, just reverse the order. Okay, otherwise then you need to actually sketch the curve though, which is no, I don't think I want to do that. Okay, yeah, this is not really appropriate way to look at that, but just a little secret for us. Now, let's say for example I do number 32. Number 32, we have the curve is given by x equals to t squared minus 2t, and then the y equals to square root of t, and bounded by the y-axis. Hold on. The y-axis, I need to find the area to the y-axis. Hold on. I need to slow down here. So let's say the curve looks like this, okay, and so let's say the curve looks like this. Boom. Now I need to find not the area to the positive, to the x-axis, but now to the y-axis. I need this guy here. This is what I need. You see what I mean? This is what I need. Not to the x-axis, but to the y-axis. Oh, shoot. So what should I do? Well, let's find first, when will this curve hit the y-axis? How do we know? at what t the curve hit the y-axis. The y-intercept will be when x equals to 0, right? Now then I get t squared minus 2t equals to 0. When you solve that, you will get t equals to 0 and t equals to 2. Now the area to the y-axis, so instead of to the x-axis, the area to the y-axis will be integral from a to b of x dy. Is it right? That's the area to the y-axis. I hope you remember this. Now then, I put in. So this will be integral from 0 to 2. X will now be t squared minus 2t. The dy, oh, what is dy? dy dt is y prime. So dy will be y prime, which is 1 over 2 square root of t, 1 over 2 square root of t. This is 1 over 2 square root of t dt. Okay, let's go on from there. This is integral from 0 to 2. Let me take the 1/2 out so that I don't need to deal with that all the time. And then t to the 3/2 minus 2t to the 1/2. When I integrate, I get 2 over 3t to the 5/2 minus, that's 3. That's 4 over 3t to the 3/2 from 0 to 2. It's 2 over 3, 4 square root of 2 minus 4 over 3. I'm sorry, I think I make a mistake here. It should be 2/5, huh? It should be 2/5 here. It should be 2/5. This is 2/5. 4/3. 4/3, and this is 2 square root. That's 1/2, 8. Maybe I factor radical 2 out so that I don't need to deal with that. 8 over 5 minus 8 over 3. This will be negative. 15. So I get negative 4 radical 2 over 15. But we know area cannot be negative. Yeah, we know area cannot be negative. So what do? Reverse this thing. I will use red color. I will reverse this. Make it 2 here, make it 0 here. 2, 0. 2, 0. So this will be 0, this will be, negative, that will be a negative. Now this becomes positive. Okay, now let's have a look on the coordinate. Where will when t equals to 0, when t equals to 0, the position is here. When t equals to 2, the position is square root 2. But so I think the area supposed to be, instead of on the right hand side, is actually on the left hand side. So this is my assumption earlier, right? Okay. So what happened is, before I actually sketch the graph, let's imagine that the graph actually earlier looked like this. That's on the left hand side of the, yeah, it's on the left hand side of the y-axis. We can find out by plotting it a little bit. Right? Yeah, it's actually, this is between 0 to 2, this graph here is to the left of x-axis. Okay, let's curve that anyway. I want to show you that it's actually not necessary for us to see what the graph look like. Just do it first. The x is t squared minus minus 2t, and then this is square root of t. I get only that part because I believe my parameters is not true. You see, it's supposed to be from 0 to 2, right? That's what it looks like.
So why did you, or how did you know that the area was supposed to be positive for this one?
Because area has to be positive.
Oh, okay. So just in general, yeah, okay.
Yeah, the general idea that area has to be positive.
Okay,
Right?
okay.
Yeah, so let me copy, let me snip this. Put it there, give me a second. So that's the graph when t equals to 0, it's here. Now t equals to 2, it's here. Okay. Now earlier I tried to plot the coordinates. When I try to plot the coordinates, I noticed that when t equals to 0, it's here. T equals to 2 is here. Okay, but how can so the order is correct. The order is from lower t to higher t on the y, which is lower to higher, right? So the order is correct, but how can I get the area to be negative? Then the only reason is because the area is on the negative side. Okay, notice that the question is the area. The question is not the integral. Okay, the question is the area. So the only way that I can have the t is below, the t equals 0 below and t equals 2 is above, yet give me negative area, it must be because the curve is actually quote unquote below y-axis. Okay, and we can confirm that from what we see here. Okay. So from here we see that the area must be to the left of the y-axis. Now notice that, did I give you a formula for the area when we need to find the area to the y-axis? I didn't give it to you. I didn't give it to you. But I based my assumption that you know the area to the y-axis must be integral x dy with the boundary on the below, and this is the upper boundary. Okay, now knowing that, then I will change this becomes lower t. Okay, and this becomes the upper t. This guy becomes, in terms of t, whatever that is. Okay, and this guy becomes y prime dt. My point is, it's substitution after that. Okay, it's substitution after that. Now that's for the area. By the way, if you have a chance, try to do number 34. That's actually a very interesting question. I believe this is a type of question that you see quite often in a lot of tests. I'm saying that it is possible that you see the test again. You see that question in my test instead. Okay, how about arc length? The arc length that we learned before, we know that's integral from A to B. Let's give the picture first. So let's say this is the curve. This is when x equals to A. And this is x equals to B. Now, at that time, we use square root of 1 plus dy dx being squared dx. Now, if you remember, it was originally coming from square root of dx being squared, dy being squared. That's what it's supposed to look like. Right? But we cannot do this kind of integral because you have two variables of integration with only one integral sign. Okay, that's where it came from though. Okay, now then we decide, you know what, let me decide by dx squared inside the radical. At that time, we divide by dx squared inside the radical, divide by dx squared inside the radical, and I have dx multiplied by dx outside. Okay, such that then it becomes square root of 1 plus dy dx being squared dx, right? And then the dx then, the variable of integration x, give us the limit. This is when x equals to A, x equals to B. Okay, now that's where it came from. Also, we had before that if I want to integrate that with respect to y, then I will divide by dy squared inside the square root. And have dy outside here. And this is becomes y equals c to y equals to d. Okay, such that the integral becomes c to the square root of 1 plus dx dy being squared dy. Now, those two formulas are the formulas we already learned in previous chapter, or even previous chapter. Is it right? I don't remember. Oh, okay. So what happened if now instead we have parametrization? Let's use that formula again. Integral square root of dx being squared plus dy being squared. Again, this is not usable, but we parameterize the x and y using t. So let's divide by dt squared inside the radical and multiply by dt outside. Okay, now and then later on this will be t1 to t2 if the curve looks like this. Okay, so our new formula for arc length is integral from t1 to t2 square root of dx dt squared plus dy dt squared dt. That's the new formula. With that, let's say, for example, we do number 42. Or number 44. Let's see. Let's do number 44. Seems like 42 is too easy. Number 44. We have the curve will be, oh, the curve is managed by x equals to 3 cosine t cosine 3t. 3 cosine t minus cosine 3t, and the y is given by 3 sine t minus sine 3t, where the t is from 0 to pi. Okay, so what I need to do first is to find x prime and y prime. This is the x prime here. This is the x prime here being squared, and this is the y prime being squared. So there will be negative 3 sine t plus 3 sine 3t. The y prime will be 3 cosine t minus 3 cosine 3t. Okay, now then I need to find the expression inside the radicand. So x prime squared plus y prime squared. That will be negative 3 sine t plus 3 sine 3t squared plus 3 cosine t minus 3 cosine 3t squared. Oh, give me a second. Okay, then do the algebra from there. Yeah, you can do the algebra from there. this is 9 sine squared t minus 18 sine t sine 3t plus 9 sine squared 3t plus, let me continue at the bottom. I hope then you see the pattern. Okay, now you see that the first term add up to what?
To 9.
Let's add up to 9. And then minus, let me factor the negative 18 from the second terms. Okay, so inside the parentheses, I will get sine t sine 3t plus cosine t cosine 3t. Is that okay? And then for the last term, I add them up, I get what? That's another 9. Okay, put things together, I will get 18 minus 18 times. What will that be? Maybe I write it this way. Let me write it this way. The one inside the parentheses. Let me write the cosine first. Cosine 3t cosine t plus sine 3t cosine 3t cosine t. What will that be? You know what's that?
Is that like a product sum formula?
Yeah.
I don't know which one.
Okay, that's cosine 3t minus t. Which is 18 minus 18 cosine 2t. Okay, now unfortunately, what we need to integrate later on is a fugly shape. The fugly integrand looks like this. So the idea is actually simple though. Okay, I mean the idea of the integration we need to do here is actually quite simple. It's the algebra in between that's scary. Okay, so what we need to integrate later on will be the arc length will be integral from 0 to pi. Is it right? 0 to pi. Yeah, 0 to pi of square root of 18 minus 18 cosine 2t dt. Okay. I can factor the square root of 18 out. I don't know if it makes you any happier. Okay, now what do we do from there? Somewhere in the past, let me box it somewhere here. That's what we need right now. Okay, sine squared x is equal to 1 minus cosine 2x over 2, while cosine squared x equals to 1 plus cosine 2x over 2. Now the guy inside the radical, the radicand here, actually is similar to this, right? Okay, so then I will write it this way: 1 minus cosine 2t over 2 equals to sine squared t, right? So 1 minus cosine 2t equals to 2 sine squared t. Agree? So far so good? Now I can factor square root of 2 out further. That becomes square root of 36. Later on it becomes 6. And 0 to pi here. Square root of sine squared supposed to be absolute of sine t dt. Supposed to be like that. However, sine t in quadrant 1 to quadrant 2, can you imagine this? Quadrant 1 to quadrant 2, right? Sine t in quadrant 1 and quadrant 2 are positive. So in that interval 0 to pi, sine t is positive, so I can safely ignore the absolute sign. Okay? But let me write it down first. This is supposed to be like this. That's 6, the integral from 0 to pi of sine t dt. But what is sine t dt from 0 to pi? There are 2 quadrants there. 1 quadrant, the area is 1. So 2 quadrants, the area is 2. Well, you can integrate it long way if you like. Okay, so that's a nice answer, huh? Okay, now you see that for this nice answer, the one that takes us forever is really just the algebra, right? Algebra and trigonometry, but anything else is just substitution into the formula. Okay, now an interesting question. I'm a bit, I want to take a little break for myself. I would like you to do question number 48. Find the length of the loop of the curve. So the curve is x equals to 3t minus t cubed, and then y equals to t squared. Now they say it's a loop, so we expect that the curve actually looks like this. Okay? It intersects itself. Okay, so there must be a time, there must be 2 times that hits the same coordinate twice. Okay, now your question is, the big question is, how do we find those t's, t1 and t2, such that x of t1, y of t1 is equal to x of t2, y of t2. give you a hint. Okay, the x, there must be two different t's that give you the same x. They are actually, you see, so you see that x is an odd function. Xt is an odd function. Okay, x is an odd function, so it will hit 0 when it will hit the same x when it's equals to 0. When x equals to 0. So either t equals to 0 or t squared equals to 3, which implies t equals to plus minus square root of 3. Now, use that for the y's. You will see that y 0 is 0. Y of plus minus square root of 3 is 3. From there we see that the common point is when t equals to square root of 3 and t equals to negative square root of 3, whose coordinate will be 0, 3. Now, that gives us the interval of integration. So your t later on will be from negative radical 3 to radical 3. What I want you to do is I give you 5 minutes to do the setup for x prime and y prime. What you need to do is to find the x prime and the y prime. And then from there you get x prime squared plus y prime squared. If possible, you simplify that. And your arc length later on, which is the perimeter of the loop, will be integral from negative radical 3 to radical 3 square root of whatever you have here, square root of whatever you have here, dt. Okay, now let me give you 5 minutes to execute it. Again, this is number 48. So the square root of x prime squared plus y prime squared will be 3 times 1 plus t squared. Okay, I think you can integrate it yourself. By the way, I happen to see that the integrand is an even function. It's an even function. On a symmetric domain interval, on the symmetric interval. So I can actually flip that. I don't know if you learned it this way in your Calc 1, but I hope you do. That's 3 times 2 integral from 0 to square root of 3 of 1 plus t squared dt. I think that will speed up your computation a little bit. Okay, let me just finish it up. This is 6 times t plus 1/3 dt from 0 to square root of 2, I'm sorry, square root of 3. That's 6 times square root of 3 plus another square root of 0. So that will be 12 square root of 3. Now that's for the arc length. After arc length, we have a surface area of revolution. We have two possible situations. The first one is when we rotate the graph. Let's say we have a graph here, and we rotate that with respect to the x-axis. Let's say like that. Okay, now the surface area of revolution we have here was from, let's say this is x equals to a and this is x equals to b, then it will be integral from a to b of 2 pi, if you remember, y ds. Pi y ds, which if we rewrite further, that's 2 pi integral from t1 to t2, because later on in terms of t, okay, y as a function of t, the ds will be square root of dx squared, I'm sorry, not dx squared. It will be x prime squared plus y prime squared dt. That's what the ds will be. This is if we revolve with respect to x-axis. Similarly, if we revolve with respect to revolving with respect to a y-axis, will give us surface area equals to 2 pi integral t1 to t2 xt square root of x prime squared plus y prime squared dt. It actually coming from 2 pi integral x ds. Okay, that's the basic formula, and I just did substitution. Now let's do a problem, and then after that I'll let you go. The last problem for the day will be, which one is good? Oh, you know what? Number 62 is basically number 48. Number 62 is basically number 48. And the curve is given by x equals to 3t minus t cubed and y equals to 3t squared. Now the reason I picked this question up because then I can just use this. I can just use that square root of x prime x squared, x prime squared and y prime squared. That's equals to something we have earlier up there. We have that here. We have that here. Same thing, right? Okay, that's 3 times 1 plus t squared. Okay, now this number 62, we want the surface area. We want the surface area of revolution about x-axis. Okay, now we know that the curve will be from what to what? From 0 to 1. Okay, the curve will be from 0 to 1, actually different from what we have earlier. So that will be surface area equals to 2 pi integral from 0 to 1 of y, which is 3t squared. This is the formula is 2 pi integral of y ds, right? Okay, so the y is 3t squared. The ds is 3 times 1 plus t squared dt. That's my ds, which I believe you can integrate yourself. Okay. out, so dt squared plus 3 to the 4 dt, that's 18 pi times 1/3 plus 1/5. Reduced by 3, 648 pi over 5. That's 9.6 pi. Well, anyway, I will stop my lesson today. Your suggested homework from this section will be for 10.2. Suggested homework for 10.2 will be from number 1 to number 65. Just do the odd ones. Okay. Skip the question with the graphing. Skip the problems require graphing. Requiring graphing. And you can also skip the one that you need to do approximation. I think the one that requires your approximation is like number 49, you can skip that. Number 55, you can skip that. Number 57 and on, you can skip that. Okay? And approximation, skip the one requiring fraction and or approximation. Okay, that's for today. See you on Wednesday.
Bye.
Thank you. Bye.
Bye. Bye.